Good afternoon, everyone, and welcome to today's webinar titled Pump Troubleshooting, Testing Your Hydraulic Pump. My name is Taylor Colon. I am a Customer Engagement Specialist at Test Oil. I'll be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure a high-quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer your questions that you have. Finally, the webinar recording will be distributed later today along with a survey. Look for this in your email at which you registered. Let's get started. Today's webinar is hosted by Jack Weeks. Jack Weeks entered GPM's organization in January of 1997 as a CAD draftsman and a hydraulic instructor. He has trained thousands of electricians and mechanics in hydraulic troubleshooting methods. His computerized animations have made GPM's presentations and training CDs the recognized leader in the industry. Jack is a well-known speaker at many industrial conferences and symposiums. He received his education from Georgia Institute of Technology School of Electrical Engineering and the Department of State Foreign Service Institute. Jack also taught radio wave propagation for the U.S. Air Force and telecommunications equipment operation and repair for the Central Intelligence Agency at American embassies overseas. All right, Jack, if you're ready, we'll pass the controls over.
All right. Well, good morning or good afternoon, depending on what part of the country you're in. I'm in Atlanta, so it's afternoon here. I want to talk about troubleshooting hydraulic pumps today. And pumps are one of the less understood components. A lot of people think they understand pumps, but they don't always very well. And they're one of the most favorite components for people to change. That's quite often the very first thing that's done. I get many a phone call telling me that they've changed their pump and that didn't fix the problem. Do I have any other ideas? Changing the pump is not a good first step. That really should be your last resort. It's usually the most expensive component on the system. Quite often it's the one that will take the longest to change and therefore guarantee the maximum amount of downtime. It's the one that'll make the biggest mess that somebody's got to clean up, and we all know who somebody is. And most of the time, the pump is not going to be the problem, in particular if you have a pressure problem. But that's part of the trouble right there. This is my 21st year with GPM, my 32nd year as an instructor period. In that time, I've met literally thousands of people who work on hydraulic systems, and a lot of very good people, but the number of troubleshooters I've met, I could count on the fingers of one hand. What I've met have been a lot of very good parts changers, and I'm not really denigrating that. I mean, someone that has that kind of experience, that has seen components fail so many times, and they know from experience that most of the time changing this part fixes that problem. That's a valuable person to have working for you, but it's not troubleshooting. The trouble comes when our parts changer changes his part, and that doesn't fix the problem. That I see quite a bit. And of course, the next step after that is to change something else. And eventually that results in one of two things. We either get the problem taken care of and the system's back up and running like it's supposed to be, or we put ourselves in such a state that we have to call somebody. And of course, you can call us. But the biggest problem, the single most important concept that separates parts changers from troubleshooters is the difference between pressure and flow. This is always the most important concept to grasp in any of the classes that we teach, and so few people really understand it. And if that's all that you get from this webinar, if that's all you walk away with, you'll then understand hydraulics better than, in my experience, about 80% of the people that work on them for a living. Most people really don't understand the difference. Most people will use the two terms interchangeably. But the way that we explain the difference between pressure and flow is with this little schematic right here. Right? Now, I don't know what kind of level I have out there of understanding of hydraulic schematics, so just briefly, let's talk about these components here. This symbol is a symbol for a hydraulic pump. It's a fixed displacement pump. We're going to be talking about both fixed and variable displacement pumps. You notice that it's drawn round. That's because it has a shaft that turns, and anything that turns is going to be drawn round. You see an arrow that indicates an output. Notice that the arrow is filled in. That indicates we're dealing with a liquid. If this was just the outline of an arrowhead, then that would be a symbol for an air compressor. Right? But we're dealing with a liquid, so this is a hydraulic pump. Now, all the pump really does is take hydraulic fluid from one place and put it somewhere else. That's all it really does. It takes it from the reservoir. This is the symbol for a reservoir right here. You'll also notice another reservoir symbol here. This doesn't mean there's two reservoirs. Just to eliminate clutter in the system, when we make drawings, we'll draw a reservoir symbol anywhere that there's a tank line from a particular component. And so the fluid comes from the reservoir into the pump, goes out of the pump and into the system. And anytime you're tracing the hydraulic flow on a schematic, when you get to a T in the line like this, you need to follow it in both directions and see which is the path of least resistance. Hydraulic oil, like a lot of people I know, will always take the path of least resistance, whether that's the desired idea or not. So we need to find the resistance in both directions. If we go this way, we get to a square that has an arrow in it. Squares with arrows in them are going to be symbols for valves. This particular symbol is a relief valve. And you'll notice the arrow is pointing this way, and this indicates the direction of flow, but you'll also notice that the arrow does not touch the inlet or the outlet ports. That makes the relief valve a normally closed valve. It normally will block flow. Okay? And I know electricians are accustomed to just the opposite. Normally closed electrical switch normally allows flow. But hydraulic symbols, normally closed valve normally blocks the flow. And something has to happen to open it. Right now, what's keeping it closed? This symbol here, this jagged line, indicates a spring. And a good way to think about it on the schematic is think of the spring pushing the arrow up, which means something has to push harder down than the spring is pushing up in order to open it. Right? This dotted line right here, that indicates a very small hydraulic line. Typically a drain line or a pilot line. This one's a pilot line. All right, and whatever pressure is in this line will also be present in the pilot line. Right? That's a law of physics called Pascal's law. So looking back at the spring again, you'll see a 45-degree angle arrow. Right, and that arrow on any hydraulic component indicates that it is variable or adjustable. So whenever you see that on a hydraulic component, you know it's adjustable. More often than not, that component is going to have a knob on it, something for the knob turner to get his mitts on. Every plant I've ever been to has at least one of those. The knob turner's name is usually not me. Who messed with the knob over there? Well, not me. And the last time that not me got a hold of this knob, he set it at 500 PSI. So that's the resistance that we have in this direction. That has to be overcome in order for oil to pass this way. Okay? Now, in the other direction, we get to a symbol that looks kind of like a bow tie. This is a symbol for a manual valve. Could be a hand valve, typically a ball valve or a gate valve or a butterfly valve. They can be open, they can be closed. This one's open. We illustrate that by showing it not filled in. So if it's properly sized, it doesn't add any resistance to the system. Downstream, we have a 55-gallon oil drum with the top cut off of it. So what would the path of least resistance be? Well, obviously, it would take less resistance for oil to travel to the drum than it would to travel through the relief valve. So if I turn the pump on, you'll see that The well goes to the 50-gallon drum, and see the gauge symbol here. You'll notice the gauge reads 0. Right, well, does that mean I need to change my pump? Well, of course not. However, how many times have you seen a pump change for no other reason than because the pressure was low? I personally have seen it hundreds of times. But the reading on the gauge in and of itself is no indication whatsoever of the condition of that pump. You need some other reason to change a pump. Right? So, suppose I close that hand valve. All right, now what's going to be the direction of flow? Well, the only direction we have left is to go through the relief valve, so that's what's going to happen when I turn the pump on. Pressure on the gauge is going to build because of the resistance it encounters. The valve will open, it goes back to tank, and what pressure would read on the gauge? Well, obviously 500 psi would read on the gauge. So what you're reading on a gauge is not how much pressure the pump is putting out. I can't tell you how many times I've heard people say that's how much the pump is putting out. The pump's not putting out 500 psi. The pump is delivering a specific rate of flow. But it's overcoming a resistance of 500 psi. So what you're reading on a gauge is, in fact, the amount of resistance that is currently being overcome in the system. Now, with that little bit of knowledge here, now we can approach troubleshooting a pump. There are two kinds of pumps. Essentially, there are fixed displacement pumps and there are variable displacement pumps. The fixed displacement pump is illustrated by just the circle and the arrow. And one good symptom for a pump that's badly worn is excess heat. You see, whenever a pump starts to bypass and it can't deliver all of its flow, oil bypasses across the tight tolerances. There's a pressure drop across these tight tolerances, and the conservation of energy law tells us that energy that goes into the machine, if we don't use it to move a load, doesn't just go away. If it doesn't move a load, it's going to do something else. For the vast bulk of that energy will get converted to heat. So a pump that is bypassing severely will be hotter than a brand new pump. That's a good thing to check. Of course, in order to have some idea when it's overheating, you have to also have some kind of idea of what's normal. So it's a good idea to make regular temperature checks on your pumps. Now, in a case like this, we're illustrating two pumps that share a shaft. We have a single drive motor that turns both of these pumps. And in most cases, these pumps should be fairly close to their temperature. They're going to be sized for the system. They're going to be under pretty much the same strain. They just do two different jobs. And while it is possible that one pump is working harder than the other and will be a little bit hotter, if we see a difference this big, say a difference between 150 degrees Fahrenheit and 120 degrees Fahrenheit, that's a pretty good red flag that something's wrong over here. Okay, so that's one good way to troubleshoot a pump. Check the temperature. But again, unless you have some idea of what's normal, then you may or may not be able to tell when it's abnormal. Here's another good way. Check the current draw on the electric drive motor. Now, the horsepower that's developed by a hydraulic pump can be expressed in this little formula: flow times pressure. Right now, the formula will change a little bit depending on what units of measure you're using, but to determine horsepower, we would multiply the amount of flow the pump delivers by the pressure that it's or the resistance it's overcoming in the system, and that will tell us the horsepower that is developed. But essentially what we want to get out of this is that if either one of these goes up, the horsepower goes up, and if either one of these goes down, the horsepower also goes down. And that'll reflect on the current draw on the drive motor. Okay? And as we all know, it doesn't take nearly as much power to turn a worn out hydraulic pump than it does to turn a brand new one. So when a pump is badly worn, its output will be reduced, even though it may be maintaining pressure in the system, its flow might be reduced. So if the flow drops, then of course the horsepower is also going to drop. Now that is not the only thing that can make a drop in current in here, but it's a pretty good indication of the condition of the pump. The trouble is that unless you have some idea, like with heat, what's normal, then you may or may not be able to tell if your current draw is abnormally low. So it's a good idea when the system is working like it should to record the normal current draw, and of course that will change as things change in the machine. You know, if you watch the gauge and if you see your gauge go up and down and you have a current meter attached, you'll see that the current draw will also go up and down. So record a minimum and a maximum current draw when you know it's working right, then compare it when you think there might be a problem with the pump. That's a pretty strong indication that the pump is bad. Now, a variable displacement pump is used in a system where the volume requirements change. Fixed displacement pump, a lot of people call it a dumb pump. It delivers all the flow all the time. It's used in applications where we either need flow or we don't need flow. Usually it's a very simple system, maybe has only one or two actuators. It's quite often used in designated cooling and filtering circuits, but the variable displacement pump is going to be used when we have a lot of actuators and when our system flow needs change on a regular basis. The pump can respond to it. Now there are single direction pumps and bidirectional pumps. We're not really going to talk about the bidirectional pump. Let's talk about the single direction pump. We don't really have time to talk a whole lot about the bidirectional pump, but a lot of the same principles are going to apply. All right, let's look at the difference in the symbol. Now we still have a circle because it still has a pump shaft, and we still have a filled-in arrowhead because it's still delivering a liquid. But one big difference is this 45-degree angle arrow that goes through the center of the pump. All right, now what did we say that means? Well, that means that something's variable. In this particular case, that means that this pump is able to vary its output. With a fixed displacement pump, the only way to vary its output is to vary the speed of the drive motor. But with a variable displacement pump, we can have a drive motor that turns at a constant speed, and the pump can stroke or de-stroke to deliver exactly the amount of flow the system needs. Now there are a number of ways of doing that. Some of them can be manually stroked, some of them are horsepower controlled. The vast bulk of them that I run across are pressure compensating pumps. And this is a symbol for a pressure compensating pump. And most of the larger systems that have a lot of actuators, this is what's going to be used. The variable displacement pump symbol is usually going to have a box drawn on the side of it. And inside the box, it tells how the pump varies its flow. This particular one has a vertical arrow. Right? Hydraulic symbols, a vertical arrow always means pressure compensating. Right? If you see this same symbol on, say, a pressure compensating flow control, that tells you that flow control is pressure compensating. But now what does that exactly mean? All right. What it means is that the pump will use the pressure in the system to determine whether it's delivering enough flow or too much flow, and it will adjust itself accordingly. In other words, you set a pressure on a pressure compensating pump, and the pump will stroke and de-stroke as necessary to deliver exactly the amount of flow that the system needs to maintain that pressure. Right? This pump is the culprit right here that keeps people from understanding the difference between pressure and flow, or more to the point, thinking that the pump pumps pressure. And quite obviously, if there's a knob on the pump, and if you turn the knob, the pressure changes in the system, then apparently that pump is pumping the pressure, and you're determining how much pressure it pumps. Well, no, that's not what you're doing. What you're doing when you adjust a pressure compensating pump is you're adjusting the point at which the pump will stroke or de-stroke to increase or decrease the flow. Right? And when the system pressure is below that setting, the pump is going to deliver its maximum volume as long as the pressure is below the compensator setting. Now, once the compensator setting is reached, then the pump will de-stroke and deliver only the amount of oil that's required by the system. Right? Well, now, how does it do that? It depends on the type of pump that you have. And the amount of flow that it delivers can always be measured with a flow meter. Right? These are not used as often as I'd like. This is a valuable tool right here, and it gets ignored. I'm sure that to include one in a system is not the best way to be the low bidder to make that system, but it is an excellent way of indicating to someone how the system is performing. And I want to talk a little bit about these. You might want to consider installing some of these in some of your systems, because the cost of these is negligible when you start comparing costs of things like downtime and unnecessary parts costs. Right? But a good place to put one is in the K-string. Okay? Let's go back to that slide here. You see in the symbol, we have a dotted line that goes to a little tank symbol here, a little separate symbol from the inlet. That indicates that that this must be a separate line to tank from this one. We can't just connect this line into this suction line. The K-string is the line where oil that has bypassed across the tight tolerances inside this pump gets back to tank. We have to do that on a variable displacement pump. We don't do it on most fixed pumps because it's not a problem. A fixed pump is always delivering flow, and if it's bypassing, and of course even a brand new pump bypasses to some degree, whatever bypassed oil goes across the components in a fixed pump will just go back around to the suction side and go right on through the pump. Can't really do that with a variable displacement pump. With a variable displacement pump, since it varies its flow and it goes anywhere from 0 to full flow, then it's entirely possible that this pump could be bypassing more than it's delivering. That means the fluid has nowhere to go that bypasses across the tight tolerances. It gets stuck there in the pump case, and pressure would build and blow out the shaft seal. So that bypassed oil gets delivered back to tank through the K-string to keep pressure from building against the pump shaft seal. Right. Now, a real good place to put one of these flow meters is in the K-string line. We usually recommend that you install one of these in your K-string line, and once a month, write down what it says. Why does that help us? Well, as the pump as the pump wears, I shouldn't say fails yet, but as the pump wears, what happens to the tight tolerances inside there? Well, tolerances get bigger. So as the tolerances increase, what do you suppose happens to the case flow? Obviously, that's going to increase as well. So when a pump is brand new, it's going to have very little case flow. As the pump wears, it's going to have more and more. All right, well, how much is normal? That will vary by the pump. You can, of course, download the file from the manufacturer that will tell you all sorts of information like that. But as a rule of thumb, most pumps are going to bypass about 1 to 3% of their total pump output when they're brand new. And as they wear, that's going to increase. Now, if we had, for instance, a 30-gallon per minute pump, then 9/10 of a gallon a minute and below would be an acceptable amount of case flow when the pump is fairly new. As the pump wears, we get more and more. And in general, and it's not hard and fast, but for most pumps, if this figure ever gets to 10% of the pump flow, or for a 30-gallon a minute pump, that'd be 3 gallons a minute, then it's probably getting time to replace that pump. Okay? So tracking the condition of that pump is a real good idea. That way we're not surprised when a pump fails. A lot of people think that a pump is like a light bulb, that it works great until it breaks and then it's no good anymore. Well, that's simply not true. Pump wear is a very gradual thing, very easy to track. Yeah, there are catastrophic failures. It does happen, but it's usually pretty obvious when it does. We're usually going to make an awful lot of noise. It's often going to blow out the shaft seal and shoot oil everywhere, and it's not going to move anything, and pressure is going to be very low, but that's pretty rare. It doesn't just happen. The pump's not usually going to be fine today and just wear out tomorrow unless something makes that happen. Most pump wear is going to be a very gradual thing, and if you track it, then you can change that pump during a scheduled outage instead of having to interrupt production. Okay. All right, let's look at how it works inside the pump. Now we're going to be talking about a piston pump. Obviously vane pumps are going to work somewhat differently, and there are other types of pumps as well. But due to time constraints, let's talk about the most popular one, which is the piston pump. Let's look at the components here. You see that we have a shaft, and as the shaft turns, it's going to turn a barrel, and the barrel is going to have pistons mounted in there, not unlike bullets in a revolver. This particular one we're showing only has one piston, and I do that to illustrate how the piston strokes. Obviously, piston pumps have more than one piston. You see a real big problem here, that the output is going to be periodic. We're going to have an awful lot of surge in between there. The more pistons we have, the less that surge effect is going to be, and the more continuous the flow. But let's look at it with just one piston right now. Now you see the barrel as it turns. The piston is connected physically to a swash plate, a cam, if you will. And as the barrel turns, that's going to cause the piston to stroke in and out. Right? As the piston strokes out, flow comes in. As the piston strokes in, flow is delivered to the system, as long as the swash plate is at an angle. Now we have a spring that's holding the swash plate at its maximum angle. And you see we have a little cylinder over here that can change that angle, opposing the tension of the spring. Now, this piston is not going to make a 100% seal in the barrel. Depending upon the pressure drop across it and how badly worn the pump is and the temperature of the oil, the amount of oil is going to bypass across this piston. It's going to go into the pump case, and instead of building pressure and blowing out the shaft seal, you see that it will go out the case drain and back to tank. You notice that the case drain is on the top. Seems like it would drain better if it was on the bottom, wouldn't it? Well, it probably would, but if we had the case drain on the bottom, then whenever we shut the pump down, all the oil would leak out. We'd start the pump up dry. So it helps our lubrication for the case drain to be mounted on top. Something to remember whenever you install a pump, because most pumps are going to have a plug on the side and on the bottom where you get it installed with the case drain. Always install it at the top, and then you're sure. If you have a positive head, then by that I mean that if the level of the oil is above the level of the pump, it probably doesn't matter. But just to be sure, it's a good idea to mount the case drain on the top. Okay, now let's look at it with several pistons. A real piston pump's going to have several pistons anyway. And the way it's arranged now, while one piston is stroking out, there'll be another one stroking in. So that gives us a much more continuous flow through the piston pump. So, now, at the maximum angle of this swash plate, the pump is delivering its maximum flow. See that our system pressure is 800 psi. This is the compensator valve right here, the one that gets adjusted. It might be hard to see here in the animation, but there's a spring symbol here, and it has that 45-degree angle arrow going through it, just like the relief valve symbol had. All right, now it's currently set at 1200 psi, so since that's below the system pressure, the pump is at full stroke. But if we get up to the compensator setting, this valve will shift. All right, now looking at the valve, see we have two squares here. And the squares have an arrow and they have a little T there indicating a block port. As long as the system pressure stays below 1200 psi, the valve is going to be in this position. And you see that any oil that was in the destroking cylinder would get drained back to tank. But if the system pressure reaches 1200 psi, then pilot pressure is going to act on the valve and shift it into this position, which you see would direct flow into the destroking piston. Okay. So let's say that we've just turned our system on, pressure is building, we're up to 800 psi, the pump is going to stay at full stroke, and then we get up to the compensator setting. Our valve shifts. That directs pressure here to the destroking cylinder, reducing the angle of the swash plate and reducing the flow that the pump delivers, because now our pistons don't have as far of a stroke because of the reduced angle of the swash plate. Okay. And if the system pressure drops, and that of course would happen if we started another actuator moving and demanded more flow, then the pump would stroke a little bit further to maintain this pressure. If we close the valve and reduce the demands of the system, then our pressure would start to build. Well, we're going to de-stroke again, and that would reduce the angle of the swash plate to limit the flow. And of course, if we block the flow altogether, we close all the valves, stopping the machine, but leaving the pump running, then the pump will fully de-stroke. And you see that the swash plate angle is full vertical. See that the pistons are not stroking at all, even though the barrel is still turning, the motor's still turning. The flow has been reduced to zero because it's currently blocked. The only thing coming out of the pump is whatever bypasses across the pistons, but it will maintain the compensator setting in the line. All right, I want you to think about this for a moment here. What would happen if this valve stuck like this? If the valve stuck like that, then the pressure would drop as soon as we demand flow from the pump. Okay? The pressure would be down to zero, the pump is not delivering any flow. What would everybody want to do? Well, of course, they want to change the pump. Now here's the thing. If we did change the pump, that would still fix it, wouldn't it? Because a new pump comes with a new compensator that's not stuck. I mean, you still messed up, just nobody knows it. Well, one guy knows it. The guy who rebuilds your pump, he knows it. And of course, he'll call you up and he'll tell you that no, the pump didn't need to be rebuilt. It just had a little trash in the compensator. I've cleaned it out for you, and I'm going to send it back to you for no charge. Yeah, right. Now, what she's going to do, you're going to get a $4,000 paint job on your pump. Okay? Now, what would it actually take to cause this valve to stick like this? Surprisingly little. Let's look inside that valve and see what's in there. Now, this is a typical pump compensator. This one came off of a Vickers pump, but they all work pretty much the same way. Typically, there's 4 little Allen screws that it takes to remove it. This valve is about 6 inches long or so usually. This hex adjustment here, this is how you adjust it. And if you pull it all the way off, these are the components that you'll find inside. There's going to be a spring. There's going to be a backing plate and a valve spool. Okay. Now look at that valve spool. You see right here a small orifice. This orifice is about the size of a small paper clip. You could stretch it out and run the paper clip through the hole to clean it out. But if this hole gets plugged up, and it takes very little trash to do that. If that hole gets plugged up, that's exactly what's going to happen. The pump is going to do this. Right now, it's also possible for it to stick the other way, where the pump stays at full stroke all the time too. But this is most likely to happen, is that we'll get plugged up over here, and the pump will be stuck in a position where it can't stroke. Okay. Do you think this has ever happened at your plant? I've literally seen it hundreds of times. The pump gets changed and it fixes it. That's great, but you could have fixed it a lot cheaper and a lot faster, because how long would it actually take to do this? How long would it take you to remove these 4 Allen bolts, these Allen screws here, open this up, dump these out, and look at this hole? Okay, granted, you have to lock it out and everything. You got to do that for whatever you're doing, though, so we can't really count that. You could probably do this faster than you can walk over to the storeroom and see if you've got another pump. Okay? Probably talking just a few minutes here. So at the very least, before you change a pressure compensating pump, pull the compensator spool and see if this is plugged up. You might save a $15,000 or $20,000 pump by doing that. Right now, here is the most definitive check of a pump. This will tell you with 100% accuracy, is the pump any good or does it need to be replaced? Right, you see we're using a fixed displacement pump, and we've closed this hand valve, blocking the flow so that the only way for oil to go is across the relief valve. Now, we've installed a flow meter in the line, in the pressure line here, so that anything that dumps across this relief valve goes through the flow meter. If this pump is bad, then it won't be able to deliver flow under pressure. It will be able to deliver flow if it's not under pressure, however. Now let's remember the tolerances in a completely worn out hydraulic pump are much tighter than those of a brand new water pump, for instance, that cannot deliver its flow under load. Consequently, if we close this hand valve right here, sorry about that. If we close this hand valve right here and turn the relief valve down very low, if we have a 30 gallon a minute pump, it's going to deliver 30 gallons a minute. Okay? If we increase this pressure though, and the pump is badly worn, it's going to lose flow. Okay. I see that when I drew this, I mistakenly left the arrow and the case drain line in here. Let's pretend that's not there. Okay. This is a fixed displacement pump. Obviously, this wouldn't work with a pressure compensating pump because the pump would de-stroke, or would it? If we have a pressure compensating pump, we can make this same check. If you turn the compensator all the way clockwise, then the pressure compensating pump is going to behave just like a fixed displacement pump. It's going to deliver all of its flow all the time. It's not going to be able to de-stroke. Okay? So, if it's a fixed displacement pump, just block the flow, turn the relief valve down very low, turn the pump on. If it's a pressure compensating pump, turn the relief valve all the way down, the compensator all the way up, turn the pump on, and even if the pump is completely worn out, it's going to show its maximum flow here on the flow meter. Okay? Now, if the pump is any good, we should be able to turn that pressure up on the relief valve and not lose any significant amount of flow. Right? I'm talking maybe just a couple of percent. Okay, so the pump's good. Flow is going to stay high even when we increase the pressure. Now, if you can get up to your normal system pressure with no significant reduction in flow, then there's nothing wrong with that pump. Your problem is elsewhere. Right? By the same token, if you turn it up and the flow drops, then the pump is bad, has to be replaced. There's no ifs, ands, or maybes about it. It's 100% definitive. You know how many systems I've ever seen with this installed in it? None, except for the ones where I've recommended it and people have taken the recommendation. To me, this is an invaluable tool. I don't see any reason why every system wouldn't have one, particularly if you have one of some of these more expensive pumps, the $50,000, $60,000, $70,000 pumps. Putting a pump like that in there and not including a flow meter, to me, that's a lot like finding a deal on a Lincoln Navigator because it didn't have a speedometer. You know, you save just a few $100s here by not doing that. This few $100s will pay for itself very quickly and reduce downtime because you can make this check in under 1 minute if the flow meter is already installed. So if you think you might have a bad pump, valve it off, run it through the relief valve, turn it down very low, see how much flow you get, then compare that to what you get when it turned up very high. You'll know in no time. Now, if you don't have a flow meter, you're not dead in the water, but you do have to be able to answer a couple of questions here. One question you've got to be able to answer, do I have a pressure problem or a volume problem? Now, 80% of the people can't answer that, but everybody that's been watching this webinar can, because you understand the difference between pressure and flow. If you have a volume problem, the system's going to move too slowly. If you have a pressure problem, the system's going to stall. Okay? Say we have a volume problem. Check the relief valve tank line. If the tank line is hot, something's wrong. There should never be oil coming through the relief valve in a variable displacement pump system. If there is, that's where some of your flow is going. Check your case flow. Make sure it's not excessively bypassing. Okay, it says here to take the case drain line off. I don't really recommend you do that. I mean, you can, but it's a lot safer to put a flow meter in there. There's some serious safety issues with just taking case drain line off. I don't like the idea of putting it out to atmosphere. Check the current on the drive motor. Again, it takes more current to turn a brand new pump than it does to turn a worn out pump. But of course, check the minimum and the maximum current draw. Make sure that the compensator is in fact set at least 200 psi above the maximum operating pressure. Now, very seldom do I see anybody turning pressures down. Mostly I see people turning pressures up. But what I do see on occasion is that a pump gets installed and everybody's warned, do not touch that pump. Nobody does. Well, here's the thing about a spring setting. Springs can never gain tension. Springs can only lose tension. So the effective setting is going to drop. Make sure that it is set above at least 200 psi above your maximum load pressure. All right, let's say we have a pressure problem. If we have a pressure problem, if it's very low, it's probably going to be the relief valve. All right? That's going to be the most common cause. Usually the relief valve will get stuck open or partway open, and that will cause us to have a pressure problem, but very, very seldom will it be the pump. Compensator might be bad, like we talked about before, but it's probably not going to be the pump causing a pressure problem. And if you just want to be sure, check your case flow. If the pump is so badly worn that it can't get up to pressure, how much of the case flow, how much of the pump flow would have to be going across the case drain? Well, almost all of it. Thing is, your case drain is usually not big enough to handle all the pump flow without a pressure drop, so the pressure drop across the case drain would cause enough of a pressure buildup in the pump case to blow out the shaft seal. Well, if it does that, we got oil shooting everywhere, and it doesn't take Einstein to figure out it's got a bad pump. But if it doesn't, if it's not blowing oil out of the shaft seal and it doesn't sound like a bucket of bolts, it's probably not the pump causing a pressure problem. Any questions from anyone?
All right. Thank you so much, Jack. At this time, we will open it up to any questions. All right. Looks like we do have a few questions here.
Okay.
All right, Jack. How can I tell if my pump is fixed or variable displacement?
Okay. That's a pretty good question. The easiest way to tell is if it has a knob on it. If it doesn't have a knob on it, then it's probably going to be a fixed displacement pump. The knob turner, of course, doesn't like the fixed displacement pump very well. But if it's a variable displacement pump of any type, it's going to have adjustments on there. So that's how you can tell.
All right. And another one. Isn't it possible that something other than a bad pump can cause a current draw to the drive motor drop?
It certainly is. The current draw is often a strong indication of the condition of the pump. However, like I said, if anything causes a pressure drop, then you're going to see a reduction in your current. Now, if it is in fact the pump, then your pressure is going to stay high, but your flow is going to drop. Your actuators are going to usually slow down. That may or may not be entirely noticeable, but if the current draw drops but the pressure is staying solid, that's pretty strong indication that the pump is bad. Now, if you have bypassing components in there that are causing a problem, that's obviously going to cause a flow problem as well, but you will see fluctuations in the pressure if it's bypassing somewhere else.
Okay, another question. Do hydraulic systems self-bleed?
Self-bleed. Well, some of them do. It's usually a much better idea to bleed the system before putting it in operation. An awful lot of components, a lot of servo valves, for instance, have bleeder screws that you can open up to bleed oil. I don't recommend that you go cracking connections or anything like that to bleed the system. There are components that you can install that are very inexpensive. I saw one online called Safety Bleed, SAF-T-bleed, and that one can be installed anywhere in the system. You can safely crack that open and bleed air out of the system with something like that. But I don't like the idea of cracking a connection and bleeding air out that way. If your component doesn't have a way to bleed it out, then I would install something along those lines so that you can safely bleed it. But over a period of time, yeah, they will, almost all systems will self-bleed, but until they do, you're going to see some erratic movement. You see, hydraulic oil doesn't compress. Air does. So it's not going to be as rigid. That means that before there's any movement, the air is going to have to compress. And of course, putting air to the kind of pressures that most hydraulic systems operate, that's going to cause some other problems too. It's going to give you some heat problems, and it's not going. It's going to operate erratically until the air does bleed out. It's kind of like if you ever have air in your brake lines, you have to pump your brakes. That's the kind of thing you're going to see in a hydraulic system.
All right, let me see here. All right, another question. Would a worn pump cause cavitation based on the lack of suction or just the lack of pressure and flow?
Just a lack of pressure and flow. To understand that, you need to understand what cavitation is. A lot of people confuse cavitation with aeration. But cavitation is a very steady, high-pitched whining sound. And it's caused by the pump trying to deliver more oil than it can get in. The pump is what we call a positive displacement device. It's going to make an attempt to deliver a specific amount of flow every time the shaft is turned. And that, of course, presupposes that you can get that much oil into the pump. Now, anything blocking the suction line could cause it. Most common cause is a plug suction strainer, because they're kind of out of sight and out of mind down underneath the oil. But what happens here is the suction pressure drops so low that it will pull air molecules out of the oil. And these air molecules get brought into the pressure side of the pump, and the sound that you're hearing is the sound of these air molecules imploding against the pump. If the pump is badly worn, then it's not strong enough to cavitate. You know, most people think they hear a pump cavitate, oh, we got to change that pump. A lot of times they change it and the cavitation goes away. Well, what happened was they fixed whatever was blocking the suction line by changing the pump. If a pump's strong enough to cavitate, it's probably strong enough to do its job. If you can correct the problem, it's reduced its lifespan to some degree, depending on how long it's been cavitating. But usually if it can cavitate, it can do its job.
All right, another question here. Is pump surging an indication of contamination in the pressure compensating spool orifice?
It can be. Of course, there are a lot of things that can cause pressure to surge, but if you did have trash in there and the spool can't shift properly, then it can certainly cause pressure surges. What will often happen is the spool sticks and the pilot pressure continues to be applied to it, and it'll break loose, and then you'll see your pressure jump up when it does that. So it can indicate, it's not conclusive that it's that when you have pressure fluctuations that it's the compensator, but the compensator is certainly something that can cause it.
All right. It looks like there are a few more questions, but I think they would be best answered through email. I would like to thank everyone for joining us today, and thank you very much, Jack, for presenting.
All right. I appreciate you having us. If you go to our website, if you'd like to see tips like this, you can sign up for our newsletter. It doesn't cost anything, and every month we send them out, and we have announcements there. But I appreciate the opportunity to do this, and thank you very much for having me.